Okay, welcome to another video. In this one I'll show you how to solve problem 6 of the sample final. We're given a connected undirected weighted graph with non-negative weights, and we need to find and also given a vertex v. We need to find a tree of g such that the cost given here is minimized. What is this cost exactly? So C of t, I want to call it, it's the max for w in v of CBW. So this is saying, given some sort of graph, okay, let me draw some graph, and this is, say, it's V, then we need to minimize the cost of the maximum path. So let me actually name these A, B, C. So we have how many paths to each edge? Well, I have one path here, I got one path here. There's actually a bunch of them, there's a lot of them. So I'm not going to actually draw them all, but you see, for V to B, I can get to V directly, or I can go through A, B, A, C, B, and so on. So what we do is consider all spanning trees of this graph, okay? And there's a lot of them as well. I'm just going to give a sample. So if this is my G, then the set of all spanning trees would be something like this one. I have B to A to C to B. This is one spanning tree. And maybe I should also give them numbers, like 2, 1. So it says all non-negative, which means yeah, so this is fine, I guess. No, I'm just gonna make this one 3. This is 1. Okay. Alright, so 2, 3, 1. This is one of them. Another spanning tree could be, we should have something like B goes to A, also goes to B, and then this goes to C. And we have 2, 1, 3, okay? And there is many more. There is many more spanning trees. But what's the deal here? The deal is that we need the tree that minimizes the cost above there. So what is this cost? Let's compute it. What we have to do is first compute the cost CVW for all edges and pick the maximum of them. So what is the distance from V to A? It's 2. The distance from V to C is 5, because 2 plus 3. The distance from V to C is 5 plus 1, which is 6. So then the maximum cost, the maximum distance is 6. So this is the answer here. What about this one? From V to A is 2, from V to B is 3, from B to C is 4. Okay? So once I have computed the maximum for all of these spanning trees, then I should return the smallest one. So this would be the smallest in this case, but actually there could be smaller ones if we continue the tree. Okay, well, I believe this is the smallest. So like we have, there's a whole bunch of spanning trees that I have not shown you. Could be there's any one smaller, but I'm not really sure. The point is, this is the smallest one among the ones we have over here, and the algorithm should find this. So clearly the answer would be something similar to Dijkstra. In fact, it's pretty much Dijkstra. Oops, go back. Yeah, so here the algorithm that would solve this is in fact just Dijkstra, because we're trying to minimize one path, but Dijkstra minimizes all paths, okay? So this is a specific problem of Dijkstra, okay? So here we're minimizing just the maximum path, okay? But Dijkstra minimizes every path from V to every other vertex. So intuitively, Dijkstra solved this, okay? And the only problem we have is that when we covered Dijkstra in this course, the input graph was directed. Now it's undirected. So you have to do some conversion before you run Dijkstra. Okay, and so the algorithm would be convert G from undirected to directed as follows. Okay, you construct a graph. This is undirected, or directed, of course, maybe directed. G prime equals to V E prime, where E prime is as follows. If UV in E, then construct, well, with weight W UV, then I'll construct two edges, UV and VU, both with weight WUV. Okay, so this is how we construct the graph G prime, and then simply run Dijkstra single source shortest path on G prime and return the shortest path tree constructed by Dijkstra. Okay, so the conversion takes E time, big O E time, and Dijkstra takes big O E plus V log V time. So the total cost, so the total time complexity is basically this stuff above, like all of this. All right, hopefully this was helpful, and see you in another video.